So we finished last time with a sort of theorem which says that if we take so let's say omega delta is a sequence of discrete domains which converges to omega. So those are discrete mesh delta, and we choose them with boundary points, let's say delta B delta C delta, which converge to A, B, C. So basically we can think that we have domain omega, we have points A and B, and eventually we'll be growing a CL between these 2 points. And what we do, and there is a point C, and then we approximate it by a discrete domain, which looks like that. And then we do, we define 2 functions U delta and V delta. So U delta was the probability that the point Z is right of, let's say, eta, where eta connects C to the arc AB in the uniform spanning tree rooted on AB. So we take all the uniform spanning trees which contain this arc. Obviously, they have one branch which goes from C to this arc, and exactly one, and it's the probability that Z is to the right. And then V delta is a slightly different model. We take probability that U belongs to the top tree. So this was probability for the USTs, and this for, let me denote it to UST. So it's a forest of 2 trees. So we have this sort of a forest of 2 trees rooted on AB, and so 2 UST, it's a forest 2 trees rooted at C and on AB. So that's the second one, and we have properly normalized them so that, because they are from different probability spaces, so we have to do ratio of partition functions. So we have to just put here number of 2 USTs over number of USTs. So what we proved last time is that U delta plus I V delta is discrete holomorphic, or as people say, pre-holomorphic. And this was just an easy combinatorial observation that derivative of one in direction alpha was the same as derivative of the other in direction rotated by 90 degrees. So normally in other models, if we are lucky, we expect to have the same picture, that there is some event which is discrete analytic. And then if we find such an event, we can continue exactly like in this model and prove everything. So that seems to be the bottleneck that we cannot find in most other models. We have in the Ising model, in the random cluster version of the Ising model, we have for domino tilings, we have for loop erased random walk, we have for uniform spanning tree. For percolation, it's which we will discuss on Friday, and on Monday it's slightly more difficult we find there are two functions whose sum is not exactly holomorphic, but it's asymptotically holomorphic. So it also satisfies some exact relation, but when you look at it closely, it doesn't tell you that there is Cauchy-Riemann, it tells you that there is a Cauchy-Riemann with an error term, but the error term vanishes in the limit. So the bottleneck so far in proving that some models are related to SLE is exactly finding something pre-holomorphic or asymptotically pre-holomorphic, and just sort of going a little bit fast, it's certainly easier to observe some exact discrete relation. So because if there is a discrete if there is an exact identity that A is equal to B, well, usually if you know that it exists, there is a limited number of methods how it's proved. Usually it's proved. Usually it's proved by bijection between two. Most combinatorial things, they proved by bijection between two sets like here. It might be more complicated if it's only hold asymptotically, that it's approximately holomorphic. In the limit it's holomorphic, but in the discrete setting it's with error terms. So maybe that's the way you go. So far we don't know how to do it for other models, and that seems to be the bottleneck. And unfortunately, so far we haven't come up with any other method of proving that something is related to SLE. So a priori there might be some methods, and we'll discuss at the end of the course, but we don't know. Okay, so U delta plus IV delta is pre-holomorphic, and it's pre-holomorphic with boundary conditions. So what it was? So it was that basically that U is equal 0 here, U is equal 1 here, V is equal to 0 here. So U is equal to 0 on the arc CA, U is equal to 1 on the arc BC, and V is equal to 0 on the arc AB, which is the same as normal derivative of U is equal to 0. Okay. And then what we can say that U delta plus IV delta converges as delta goes to 0 to, let's say, U plus IV equal F, which is F is holomorphic in omega, and same boundary conditions. Same boundary conditions. Which means that F maps omega to a half strip. So here is U is equal to 0, here U is equal to 1, and here V is equal to 0. So it maps to a half strip of width 1. So it's quite clear that this is the only function which is analytically satisfies these boundary conditions. One can do it either with argument principle. So with argument principle, if you have something and it has on these three arcs boundary 0, 1, and V equals 0, then when you go around the boundary, you sort of go first up and down this half line, then up left, right this interval, then up and down this half line, then you jump, and basically around every point inside you go exactly once. So it's taken exactly once, so it will be exactly the conformal map. Alternatively, you can also use uniqueness theorems for the Dirichlet functions. Now, well, proof was essentially in the exercises, so I'll just say a few words about the proof. One can do several proofs. One can, for example, prove this using the random walk. So these functions U will be just related to random walk, and basically you do random walk in the domain. And so what was so the first? So I will sketch two proofs. So the first first proof is use random walk. So if we have just two arcs and boundary values 0 and 1 for function u, then u of z is the probability that random walk from z exits through the arc, what were the letters? Let's say the arc exits through the arc BC. Now, so that's essentially the usual setup of Courant-Friedrichs theorem. So this is also the harmonic measure of the arc BC as viewed from Z. Now, if we do this boundary condition 0, 1 and what is called Neumann boundary conditions, so it's Neumann, then it's exactly the same. U of z is equal to probability that random walk from z exits through BC. But in this case, what Neumann boundary conditions correspond to? They just correspond to random walk being reflected on this side. So when it hits this side, it is reflected, bounced back in the domain. So it can't exit through this side. Z reflected on the arc AB. So it only can add exit through AC or BC. Here it's always reflected, it bounced back in the domain. There is a line of whatever policeman who forces it back inside. And then, well, it's just the same theorems about random walk. We'll take care of it, so it will converge. So it's then this will converge as delta goes to 0 to the same probability for the Brownian motion. So it's u small z. Now, how is this related to half strip? Well, for example, the first domain, the easiest way to see the probability to exit through the right arc is just to map to a strip. And then you are looking for a harmonic function. So we know this tiny theorem, this harmonic function. It's a harmonic function which has boundary values 0 and 1. So it's a linear harmonic function. So it's just the real part in this picture. Now, well, you do Brownian motion, you hit. Now, what happens with this one? Well, as I said, already going a bit fast that we go into the half strip. So what can we do if we have a Brownian motion which is reflected inside the domain? So here we'll have the same picture, so it's reflected inside. So what we can actually do, we can actually take our first strip, cut it by a line, and then reflect the Brownian motion. So what we can do, we can actually do Brownian motion in the strip, and then reflect everything around the line, and we get Brownian motion in a half strip. So it's, well, take BM in a strip, reflect all excursions below the line y equals 0, and you get you get reflected Brownian motion. So in this case, it will be something like that. So basically, we reflect and then we erase this part. So essentially, then what you get in this case, that probability that you end up on this part is just the probability that the original Brownian motion ended up on the whole right line. Or probability, for example, that if you want to calculate something more interesting, like probability that we ended in this interval, then you have to do reflection. It's the probability that we had in this interval on its mirror image. So you can easily reduce it to the previous problem, but doubling your set. So this is the proof. If you are probabilist by education, then this is more comfortable proof, because you know that random walk converges to the Brownian motion. Now, well, there is this dead general theory that well, everything in potential theory you can either do with the harmonic functions and potential theory with Brownian motion. So obviously there is a proof with the harmonic functions. So it's just well, again, it was outlined in the exercise, so I'll just say 2 words that U delta is discrete harmonic function. Just from Courant-Friedrichs-Levy theorem, we can deduce that it will converge. So there, one of the, perhaps the most difficult part of convergence was that you first show some precompactness, that they are, say, uniformly continuous. So in our case, we can do a shortcut, because we can deduce precompactness from properties of the uniform spanning tree. So we know that this branch is actually a loop-erased random walk. So if we want to calculate our function difference of values at, say, z1 and z2, it's just the probability that loop-erased, it's bounded by probability that loop-erased random walk passed between the 2 points. And loop, it's basically can be bounded probability that random walk hits the cut between these 2 points, which is harmonic measure of this cut in a big domain with this cut. So it's small in the size of this cut. So you get from this Hölder continuity. So basically it's a harmonic functions converge. So just use this Friedrichs Levy theorem. So there is a shortcut can get continuity or uniform continuity, not from Harnack, which we can easily do because function is between 0 and 1, but from UST properties. And this is again the thing with most of other models. If you define some discrete harmonic functions through probabilities in the model, usually you can see that it will be nicely continuous or nicely Hölder continuous, just because you can estimate probability in a model. So it's u of z1 minus u of z2 is at most that probability that loop-erased random walk from C hits the interval z1, z2, which in turn can be if loop-erased random walk hits, then the random walk hits before loop erasure. So it can be bounded as the so it's bounded as by the same thing, probability that random walk hits, and that you can bound. Let's say I will just write this sign z1 minus z2. If you are far away from it, because this is just the basically harmonic measure of this cross-cut in this domain. Okay, so that's the sketches of the 2 proofs. So I didn't say on purpose what I mean by convergence of the domains, because if you really want to do all the details, it gets a little bit ugly. And I didn't want to go too much into ugly details today. So I'll just do a remark. Okay, remark. Omega delta converges to omega. We by this we mean what is called Carathodory Convergence. Now, so Carathodory was a Greek mathematician who was quite active in analysis, in functional analysis, and complex analysis. He has an accent somewhere. I think he has an accent here. And I don't remember which one, him being yeah, I should check. So basically, Carathodory convergence is a convergence from the point of view of a conformal observer. So what you do, you fix some reference point. So it's convergence for conformal observer. So basically what you fix Z0 inside omega, or Z0 on the boundary of omega on some smooth patch of the boundary, smooth part of the boundary. And then basically you take, well, okay, so this is domain omega, this is domain omega delta. So we take uniformization phi, which goes from omega to the unit disk. But yet it's the other way around, unit disk to omega and Z0 to Z0. Or if we fix boundary point, then you have to, or one goes to Z1. And you do phi delta the same, bless you, to omega delta. 0 goes to Z delta, Z0. Let's say Z delta. So convergence, so Carathodory convergence is, so we write that omega delta converges in the Carathodory space if phi delta converges to phi uniformly inside the unit disk. So the conformal maps converge. So what's the difference with the usual convergence of domains? So it's weaker than the usual convergence. So if you have a picture like the one I drawn, that the boundary is within epsilon neighborhood, then it will imply Carathodory convergence. It's not very difficult to check that if you have domains, if you fix point inside away from the boundary, and if you have domains so that their boundaries within epsilon of each other, conformal maps will be within epsilon of each other. But so it's if boundary of omega delta converges to boundary of omega delta in the Hausdorff norm, that this implies omega delta converges to omega in Carathodory. But not the other way around. In a sense, it's a weaker statement. Suppose that I have a domain which has this very thin peninsula. So from the point of view of a conformal map, how does conformal map from a disk to here see this peninsula? Basically, if I do this cross-cut, you can just look at the harmonic measure of this cross-cut. This is the probability that Brownian motion enters here. It's very small, which means that here it's mapped into something very small, because if it would have been mapped in a long arc, there would be a big harmonic measure. So it means that this whole thing beyond the cross-cut, this whole region of space, from harmonic for conformal observer is very, very small. So it's basically irrelevant if you do convergence inside. So if you have the sequence of domains which all have this peninsula attached, but you pinch this thing, then it disappears. So it's not important. So Carathodory convergence can lose whole. It can be that the sequence of domain converges in Carathodory sense, but it loses this whole kind of big part of the domain. It cannot gain out of nowhere, but it can lose. So it cannot reappear because you cannot unpinch. If you unpinch something, then, well, then you unpinch and it's visible immediately. But you can pinch and hide such things. So in a sense, this is a weaker convergence. It's more convenient to work with when you are talking about conformal maps. And since learning revolution is defined with conformal maps, we'll be talking about this. But basically, in your head, you can think that essentially it's convergence that the boundary is very close within delta distance, and also you disregard this peninsula. So this is the exact formulation is with the conformal maps. Now that's the first remark. Before we go to the proof, the second remark is that, I don't remember, I think I already said it, that what you can do the same trick, but you can fix 4 boundary points. So we can study UST rooted on 2 arcs, AB and CD. So we can study uniform spanning tree, which is rooted on 2 arcs. So it looks something like that. And that will give us a function U. And then the very same thing gives us a function V if we do these 2 USTs which are rooted on these arcs. So there are 2 trees which cover the domain, and one of them is rooted on the arc below, one is rooted on the arc above. So what we then get is that the U delta plus I V delta converges to U plus IV, which is, so this F, it maps our domain now not on a strip, but on a rectangle. It maps on a rectangle, and since U is the probability of something and V is the probability of normalized, so it will be of width 0, of width 1, but the height of it will be the limit of this coefficient. So it normalizes to interval of height m, where m, which is the modulus, conformal modulus of this, is the limit as delta goes to 0, number of forests of 2 trees over the number of uniform spanning trees. So Riemann uniformization theorem obviously can be proved with probability. You can do it by a random walk, or you can do it by UST, as we have shown that you can map it to half strip using UST probabilities and passing to a limit. But here it also shows that for non-trivial shapes with non-trivial modulus, you can get the value of the modulus and you can get the conformal map, again by counting something, and modulus then can be estimated in the discrete setting as comparing to probabilities, to partition functions, and then in the continuous by passing to a limit. So that's an observation, and you can do this also for Riemann surfaces. So you can actually, any uniformization can be done with random walk or with UST if you wish with the Ising model. Okay. Now let me formulate the main theorem. So the main theorem, I can use, so that's the main theorem, which is due to Wöhler, Schramm, and Werner. It's 2001. So we'll do a slightly different proof of it. So we take a sequence of domains which tend to a domain. Yeah, we don't need point C here. Take UST delta rooted on the arc A delta B delta and define a piano delta curve. Define, let's say, gamma delta, which is the piano delta curve. So this is the curve which follows UST, follows the uniform spanning tree from A delta to B delta using the right-hand rule. So essentially, on this picture, it does something like that, that it goes around. So on the lattice scale, it is space filling because we have a tree which visits all the vertices. So this curve will visit all the squares. So I've drawn a picture the previous time. It's not exactly important how you draw it. So it's also in this case it will be a curve which goes something like that. Also, as I observed last time, that you can also, it goes, or you can write that it's goes between UST and the dual UST rooted on B delta A delta. So it's AB. So you can also define a dual UST on a dual graph, which is rooted on those two. And then, okay, here I made small two drawing mistakes because it's not quite UST. So it goes like that. And then gamma delta converges to SLE 8 as delta goes to 0. Now what do I mean by this convergence? So we have two random curves on the left and on the right. So SLE 8 is a measure on random curves. So it's so this is so SLE 8 is the measure on, let's say, Hölder continuous curves. And gamma delta is a measure on broken lines, which are also Hölder continuous because all broken lines are Hölder continuous. So both things are measures on Hölder continuous curves, so they can be written or belong to the space of measures on Hölder continuous curves for some Hölder alpha. So this convergence is so this is in the sense, so convergence, so this is weak star convergence in this space. For practical purposes, it means that all probabilities you can think of will converge. So for example, probability that you visit this ball and then that ball for gamma delta converges to the same probability for SLE 8. So basically it means convergence, so weak convergence for measures, it means that all functionals converge and no reasonable probabilities can be written as functionals or combinations thereof, so all reasonable probabilities converge. So in practice, so it means that, remark, in practice, all probabilities converge. So the proof has, well, there are, okay, let's say proof. So the original proof of the original proofs of Rowley-Schramm-Werner uses a different observable. It works more with the Ruppert-Strand-Walk related things. And what they do the following thing. So they describe gamma delta by Loebner evolution. So any curve, any broken line can be described by Loebner evolution. Now random broken line is described by random Loebner evolution with random driving parameter. Now obviously it's not a SLE yet because you get a random curve, a random broken line. So what they do, they use observable to show that the driving force, or I don't know how driving force, is approximately Brownian motion with the speed 8. So not exactly, but approximately. Obviously it can be exactly because you have a broken line. And then show that as delta goes to 0, the driving force converges to square root of 8 bt. So, and this will be convergence which is weaker than convergence in the space I said. It's a convergence which says your driving forces converge, and convergence of curves is stronger. It's very easy to check that if two curves are close, then their Loebner driving forces are close. But the other way around, it's much more difficult. So it's because you have to solve nonlinear equation. So then you improve this to convergence of curves. So we will commute the different elements of the proof. So it's basically there is one ideologically important element where you show that the driving force is Brownian motion with speed 8. The rest are kind of, let's say, boring estimates, technical estimates. Now we will just commute them to a different place of the proof. Unfortunately, there is this principle that the total amount of difficulty in the proof of a theorem, usually it's more or less the same, but it's like a bump on the table close, you can move it from one place to another, and it's always better to isolate it as far as possible so that you see what is the main idea, and you see where there are boring estimates, which sometimes actually might be the bottleneck and might be more difficult to do. What we do, we will show that the family gamma delta is precompact. So we'll start with the boring thing. It's precompact in Hölder alpha, in the space of Hölder curves. And moreover, even better, intersection with Loebner evolutions. So it's precompact in the space of Hölder alpha curves, but also it lives on such Hölder alpha curves which you can describe by Loebner evolutions. Then we choose by precompactness converging subsequence. Let's say gamma delta J converges to gamma. And since we describe a Balaune evolution, we describe gamma by a Loebner evolution. Then show that, well, use the observable to show that the driving force of gamma is exactly equal to square root of 8 Brownian motion. And since we have pre-compact set, and for convergent subsequence we get a SLE, it means that it just converges to a SLE. Because suppose it doesn't. If it does not, then we can choose subsequence which doesn't converge to a SLE, but by precompactness, which converges away from a SLE. But by precompactness it has converging subsequence and it converges to a SLE, so it's a contradiction. So this implies by precompactness that gamma delta converges to SLE 8, and in the strongest possible sense, because it precompactness in Hölder alpha space, then it converges to Hölder alpha space and in Loebner space and everything. Okay, but essentially it's the same proof. It only uses different observables. It only commutes the difficulty away. That's again the main part is this: that how you see that it will be a SLE. Okay. Now let me maybe formulate a proposition. So it's what do we do? So I will okay, so yeah, maybe it's good time to take a break, because I'm not going to do anything in 3 minutes which remain. So the question which we'll first discuss the important part. And the important part, the ideology, is quite easy. So we have our observable, and it has a very nice property that if I trace this curve, we still have full control over it. So basically, what, for example, happens if so we'll discuss it after the break in detail. Suppose that I trace my curve up to that point. So it covered some region. So basically it means that there is a tree which grows here. And well, I went and have eaten this whole thing. So what is nice about my curve is that it has this Markov type property that essentially in the new domain, this omega minus part which is eaten, again I have exactly the same picture, that there are 2 points A and B, but now it's not A, it's, let's say, AT, and there is a root below, and I am building a SLE I'm building uniform spanning tree on this root. So my curve is just the same, similarly defined in new domain. And if I have not hit yet point Z, if it's far away, basically again I can look at the probability that it's to the right of a curve. So I can always look at this probability, but then there is a conditional probability formula which tells you that probability of event is an expectation of conditional probability. So I can sample for all possible positions of point AT, say after 100 steps or after reaching capacity T, like Loebner evolution tells. And I get that the original probability, original function U, is expectation of these functions U for new domains, which has a very specific meaning, because function U is a map to half strip. So it tells you the map of half strip to original domain is the expected value of maps to half strip for domain where you drawn your curve up to AT. So it gives you some nonlinear information on your domain at time T. And the only question is it very nonlinear so that we can deduce anything, or can we deduce something? And the fortunate answer is that yes, we can. It's actually fairly easy to do. So that we'll do after the break. So basically the main idea here is that if we have one observable, we can sample it to get enough information about the driving function. And then you should have in mind that if, for example, you have, if you're driving a car and, if at any moment you observe certain things, for example, if you observe how your steering wheel is tilted or and what is your speed, then you can reconstruct then the movement of your car. So it's actually enough at every given moment only to have basically two real pieces of information, and we can deduce them from this function. Okay, break. So I will use precompactness at will. So we assume that that is known. So let's say proof. So it's modular precompactness. So take a converging subsequence gamma delta j converges as j goes to infinity to some curve, let's say gamma prime. Converging, converging in the space Hölder alpha, but if curves can be Hölder alpha can be described by Löwner revolutions, then this will also converge in the space of Löwner revolutions. So the driving forces will converge. So in Hölder alpha, but also that implies that also driving, we don't need it, but also driving forces converge. Describe gamma by Löwner revolution, let's say with driving force, for example, Wt. It is enough to show that Wt is Brownian motion with the speed 8, so square root of 8 times bt. Because then, since we proved it for any converging subsequence and there is precompactness, then we'll have that gamma delta converges to a silly 8. So it's the usual precompactness trick. If you have that for any converging subsequence you converge where you should, and your space is precompact, then everything converges. If not everything converges, then there is subsequence which diverges, which stays away from a silly 8. We take a converging subsequence. By precompactness, it converges to a silly 8, a contradiction. So that's enough to do. Now, we can observe that f delta, which was u delta plus iv delta, has what we can call a Markovian-Martingale property with respect to curve gamma delta. So what I mean is that if we draw our curve to some time t, so stop gamma delta at time t. So time t is just any stopping time. After 100 steps, or first time you hit some curve, or when you first reach capacity. So this is gamma t. Then the original curve, the original f delta of, let's say, let me write f delta of z in domain omega is the expectation of f delta z in domain omega minus gamma 0t. Well, it's gamma, let's say, it's gamma 0t. Expectation is, so I'll abuse a little bit notation, it's taken over all possible beginnings. So what I claim is that A, B are the points, so we take Z, we take the point C, and my function sampled at point Z is equal to expectation of my function sampled at point Z in all the domains where I take these things. So indeed, this is just the, how you call it, total probability formula or something. So F by the total, or by total probability formula, What is this Fz? Well, just let's check it for function u. U of z omega is the probability that z is right of the curve eta. So it was probability that z is to the right of this curve eta. So this is our thing, which looks something like that. And this is the curve eta. So u of v was the probability that we, right of eta, where eta is branch, UST branch from C to AB. Now, this is expectation over all gamma 0 t. That probability is that z is right of eta. Well, what happens is that we run this thing. So, well, it's easier if we assume that we run it and stop at the time before it. It's z or c. So let's assume it, but it's actually it's not really important. Then it's just by form of total probability. This event is expectation of conditional probabilities. So z right of eta given gamma from 0 t. So if the first was the probability in domain omega, then nu is probability in domain omega where gamma 0 t is excluded. But the important thing is that this conditional probability is just the same probability in a new domain. Because what can happen with this branch? This branch either goes down to this arc, or it can go and land on that arc. It cannot go through this part of the boundary, just because basically it's maybe the easiest to see is with the dual tree, that there is a dual tree rooted on this part, and all so this domain which we cover is in between two trees, yellow and blue. So when we reach this point, this arc will be yellow and this arc will be blue. So our branch cannot go through this arc. It can only land either on the remaining part of arc AB or on the new boundary created so far. So it does not change. So this conditional probability is just the same probability. So it's can be written as the same probability in new domain. So it can be written as a u of z in omega minus gamma 0 t. Expectation with respect to gamma 0 t. And it will be similar in all other models that if you define any reasonable event, then it's martingale with respect to this filtration. So it's just that's it. So this is the main identity. So is it clear? So for other models, it's usually as clear as here, or sometimes we take some artificial object, but then we normalize it by the partition function to make it a martingale. So you can take some other thing which is not a martingale, but then properly normalize it so that it becomes one. So what is important is that this is a discrete identity, but it also holds for the subsequential limit. And the reason is that our boundary value problems, Dirichlet and Neumann, they are very stable under perturbation of a domain. So if I take a domain and perturb it in Carathodory metric in this, so if you have two domains and they are close, for example, if they are boundary close, or weaker yet, if they are Carathodory close, so conformal maps to them are close, then solutions, then the functions f, solutions of Dirichlet-Neumann problem are close. Why? Because they are conformal maps themselves to a strip. So if you have two domains whose conformal informations are close, then their maps to half strip also are close. So it's that easy. So since solutions of boundary value problems are Carathodory stable, we can pass to a limit. We can pass to the limit in delta. And we get that for our curve gamma, for our subsequential limit, f z omega is equal to expectation for curve gamma 0t f z omega minus gamma 0t. Just expectation with respect to gamma 0t f of z omega minus gamma 0t. So this is the main property. Now what we can do, we can use it for the Loebner evolution. So what we do, we describe gamma by Loebner evolution, the subsequential limit. So well, let's say we can move it. Well, we can draw the same domain, but let's draw it in half plane. So basically, we have this curve gamma 0t, which looks something like that. So one can think that again we have this yellow tree. So this is a space filling curve. And then there is a dual tree on the other side, which sort of fills everything. And essentially our boundary, as I said, it's no longer important, but it's yellow here and blue there. And what is a Loebner evolution? Loebner evolution, so now we choose T capacity parameterization. It's, we take map GT, which sends this tip, so the map GT, it sends infinity to infinity, so GT of z is equal to z minus wt plus 2t over z plus no order terms at infinity. So what we want that WT is square root of 8BT. So this is a big question mark. How do we prove it? And we want to pump into our information, our identity star. We want to pump into some information about WT. Now, so how to rewrite star in terms of GT. So an identity star, we had to fix some point inside the domain and some point on the boundary. So basically, we fix C on the boundary. So in this case, it's on the real line. Z inside the domain. So it's in half space. So let's, well, it doesn't really matter. Let's suppose that it is here the point C and somewhere here point Z. So they are mapped to a point GT of C, GT of Z. Now we assume that the points are very, very far away. So for a time of some order, we take points much further away. That means that will be part of these estimates which we have to do later. That means that it's very low probability that they have been eaten by now. So it's, well, for Z, the probability basically will be 0 because it's with certain capacity you can't reach that high. So for any capacity, you can just go twice higher than this capacity, and then you can reach this point at all. And for that, you can just look at some possibilities for the uniform spanning tree. Okay, so they are much further away. Now, what is our function f? Our function f is a map to a half strip. So let's write the map to a half strip, and the map to half strip which sends, so what we have, it sends the points, let's say, what are our points there? So this is point 0, so it sends point 0, let's say GT of, what is it, was C. So let me denote it by B, and let's say GT of Z is A. So we need a map which sends half plane to a strip with points A and B. Now, this map will be, what is it? So if I take the map, so this I should have given it as an exercise, but if I take the sine function, so how does the sine function map vertical half strip? So sine, if I change the argument from minus pi over 2 to pi over 2, then it changes, sine changes from minus 1 to 1. Okay. If I go further in increments of pi, it will be just oscillate between minus 1 and 1. And since so it's an analytic function, it's sort of fairly easy to see. Then if you go orthogonally, then you actually continue on this line. So this goes to that, and this goes to that. So this is easy to see from earlier formula, for example, through the running through the exponent. So sine maps half plane, half strip to half plane, Then if we want to map half plane to half strip, we need to do the inverse map, which is the arc sine. And we have to normalize because we want 0, 1. So actually the answer is 1/2 plus 1 over 2 pi. So if it changes from minus pi over half to over pi over 2, then we get what here if we put minus pi over 2. No, maybe I should arc sine is between pi over 2. Yeah. Yes, yeah, 1 over pi, I think, like that. Arc sine of and then before we do that, we also have to normalize these points so that they go to 0 and 1. So we have to divide by b. So it's it will be arc sine of z over b, if I'm not mistaken. Yeah, so it's a somehow I have different thing written here. No, wait a second. So here I go from -1 to 1. Yeah, so I need to change. Yeah, sorry. So I need to first map these 2 points -1 and 1. And how do I map points 0 and b to points -1 and 1? I map them by a map. Yeah, so this map is z. So okay, so 0 should go to -1 and b should go to +1. So it should be, let me see, b plus z over b minus z, something like that. So it's 0 if I plug in 0. No, I switch the sign. So I should, if I plug in.
Z minus b divided by b.
Sorry?
Z minus b divided by b.
By z minus b divided by b, yeah. 2z. Yeah. 2z minus b divided by b. Yes, arcs 2z minus b divided by, yeah, so if I plug in 0, I get -1. If I plug in b, I get 1. Yeah, so arc sine 2z minus b divided by b. Yeah. And why do I have a different formula here? And the reason I have different formula here is that I am, well, yeah, C is to the right, yeah. So we should actually, yeah, sorry. We should, we want boundary, what are the boundary conditions we want? We want 0 boundary conditions here, 1 boundary conditions here, and Neumann here. So this should go to the bottom of the strip. So this arc should go to the bottom of the strip. This should go to 0, this should go to 1. Now, what are our conditions there? Basically 0 here, 1 here, and Neumann here. And we want Neumann 0 and 1. And here the map with the sign was Neumann 1 and 0. So basically we have to permute a little bit. We want to move this interval into the middle. So we want to go 0 goes to 1, 1 goes to infinity, and infinity goes to -1. Yeah, that's what we want. So we want to have Neumann part here, 0 here and 1 here, for example, like something like that.
B goes.
Sorry?
B goes.
B goes to infinity, yes, yeah, B goes to infinity. Yeah, and then that is normal, then we just change the sign to flip it over, so it's, yeah, so we change the sign to flip it over, so what is, if B goes to infinity, then it's Z minus B. We divide by Z minus B, or B minus Z. It's more convenient for me. And if, so who goes, infinity goes to minus 1, so it's B plus Z, yeah. So if I plug in infinity, infinity goes to minus 1, yeah. So that's. And from that, with arc sign, we get a strip from minus pi over 2 to pi over 2. Well, 0, 0, 0, 1, 1, 1, and then we do minus arc sign to flip it over. But that's not really important. So, well, here it's not, well, minus pi over 2, pi over 2. So we have still to do a linear transformation, 0, 1, and linear transformation is what is written here. So it's yeah, if it's just arc, well, it's just arc sign. Yeah, okay. If just arc sign, it's 1, 1, 1, 0, 0, 0, and then we put coefficients, and everything becomes fine. So it's plus Z, B minus Z. So let us check. So we have numbers pi over 2 and minus pi over 2, which should become 0 and 1. So if I plug in minus pi over 2, I should get number 1. Yeah, so it's like that. And if I get pi over 2, yeah, so that's the formula, yeah. Okay, so it's not, well, all that important, but basically what we need, if we reduce something to some observable for some model, we need some formula. It doesn't have to be a formula with algebraic function. The one for percolation will be a formula with hypergeometric function, which is not algebraic. But then we'll only need to know its derivative and its value at a given point, and that we do. So here, the important thing is that we can write formula and then evaluate it. So we'll need to evaluate it at one point. So what we get is that for our new function is that we have this property f with a very, very specific value of our function. So very, very specific value. Yes? Is there a mistake? No? Yeah, okay. By the way, if I made mistake in this coefficient or in that coefficient, it doesn't matter at all, because if function is a martingale plus a constant, it's a martingale, times a constant, it's a martingale. So if I screwed up these two coefficients, we won't notice this at all. Now let's now do the main calculation. So it's a bit boring. So write the identity star, and we plug in this function. But we can simplify. We can forget 1/2 and minus 1 over pi. So we can just write it for the arc sign. For the arc sign. So what we get, well, because, so 1/2 minus 1 pi, so that we can remove. So basically, we get the formula that for our original functions, so let's say arc sign sine B, well, yeah, let's say arc sine C or B, whatever, C plus Z over C minus Z is the expectation over all curves we can draw from 0 t of arc sine gt of C plus gt of Z over gt of C minus gt of Z. So that's exactly this identity because our function f up to this factor and additional term which we removed. So our function f is a map to a half strip. Originally, when we had this thing, the map to a half strip is just arc sine b plus z over b minus z. When we removed this piece to get to map to half strip, we map by gt to half plane, and then arc sine gives us a map to half strip. So this is the original map to half strip. And at time t, when we chewed off a piece of a domain, map to half strip is first we map by gt to half plane, and then we map to half strip. So this is basically this maps C plus to half strip, and this thing maps C plus minus gamma 0 t to half strip in two steps. First GT maps it to half plane, and then this maps to half strip. So this is just a rewriting of our identity. And by the way, gamma 0 t is exactly the same information we have in the map GT, because map GT exactly keeps the information what happened up to time t. Now, what we do, we want to deduce from this some information about GT. Now, how on earth can we do it if here there is expectation of something nonlinear which involves GT, and we are essentially after this coefficient? Well, what we can use is that we have this power series expansion at infinity. So if we plug into this formula some points very, very far away, which are not swallowed by our curve so far, so that this expansion is valid, then we can simplify this. We can plug in expansion instead, and we get first two orders of this identity in terms of this expansion. So now, so what we do, we plug in very large C and Z. So very large means that they are not swallowed by our curve yet. Now there is a tricky point. So if you want everything to do everything right, so GT of Z, it's very easy to ensure that it's not swallowed. It's just if capacity is T, then if it's higher than 100 T, it's not swallowed. But our curve, theoretically, it can go very far and swallow as much of the line as it wishes. But that happens with very small probability, because our curve happened from UST, and if it goes very, very far to the right without going very high up, that essentially, so you can evaluate that those are very, very small probabilities. It, for example, would mean that there is a loop-raised random walk which follows this line without touching for very long distance. And that's very unlikely to happen. You can't have a random walk or loop-raised random walk running epsilon close to the line for 1 mile without touching it. That probability is very small. So that we'll cover tomorrow, well, Friday rather, with the a priori estimates. So we plug in very large C and Z. So let's say that yeah. For example, Z is equal to K times C, so it's even larger. So then what we get is that arc sine C plus KC over C minus KC, which is arc sine of 1 plus k over 1 minus k is equal to expectation over all possible maps GT. Now I have to plug in there the results. So it's arcsine. Now GT of C, so I plug in GT of C. It's C minus WT plus 2T over C plus small order terms. Yes? Yeah. Sorry? No? Yeah. Then the same thing here, C minus WT plus 2T over C plus small order terms. Basically, small order terms there of the order or capital 1 over C squared. And then the same thing for Z, so I add CK minus WT plus 2T over CK plus, minus CK minus WT plus 2T over CK. So now it's clear that we can expand it and we get first 2 or 3 terms up to smaller order mistake, error term. So immediately what we can do is that upstairs we have C times K plus 1 minus twice WT plus twice T over C K times K plus 1 plus small order terms. And downstairs we have C times 1 minus K. WT cancels out plus twice T CK over K minus 1, yeah. Well, let's say 1 minus K, and I then put plus or small 1 over C squared. So if you want to do, if one wants to do this 100% rigorously, we have to have an estimate of this error term when we are far away from the how. So I won't do it, but it's possible to do.
Shouldn't it be O of 1 over C cube?
Should it be O of 1 over C cube? Yes, because we divide by C. Yes, you are right, because here the main term is C. So it's when we divide both things by C, yeah, that is 1 over C cube, yeah, of course. Yeah, because here we can cancel C out. So what we get here over C squared, and the O is then 1 over C cube, and we can move it out, yes, yeah, so it's actually better. Okay, so this thing, it's obviously, I mean, you can divide Taylor series in fractions and get expansions. You can do Taylor series for the arcsine. It's an easy calculation. I mean, it's fairly easy to do by hands. You can also be done by Mathematica if you had bad grades in the calculus 101. So I will just write the result. And it's actually, you will see that it's error correcting. If you screw up the computation, then you get a contradiction. You don't get that it's SLE6 or SLE7. Most likely you just get a contradiction that it doesn't make sense at all. So you can redo it once again. So basically what you get on the right hand side, so we had arcsine 1 plus k over 1 minus k, and on the right hand side it's expectation of all possible maps GT. And obviously, since two things are equal, the first term without dependence on C is just 1 plus k over 1 minus k. So the first term will be exactly the same. Arcsine 1 plus k over 1 minus k. Then there will be term which is 1 over C. So let me write it in a different color. And the term with 1 over c is, the term with 1 over c is minus 1 over square root of k wt. And then the next term with 1 over c squared, and then there is O capital 1 over c cubed. So the next term with 1 over c squared is a bit more complicated. So it's k minus 1 over 4k square root of k wt squared minus 8t. So this is just the calculation. So it's kind of completely irrelevant. There is nothing deep here, and anyone can do it. And once again, it's error correcting, because what you see that if you do this calculation, so starting from this term, we cannot say anything. But before, we have 2 power series expansions, which coincide, or rather left coincide with the expectation of the right, and left has only 1 term, and the right has 1, 2, 3 terms, which means that they're equal term-wise. So the first 2 terms are equal, and luckily they're equal, so we haven't screwed up here. But then it also means that the next 2 terms are also equal. Well, at first it seems a bit strange how wt can be equal to 0, but we have expectation here. So actually we have 2 terms which are equal to 0 in expectation, and what we have is that expectation of 0 is equal to expectation of wt, and 0 is equal to expectation of what is it, wt squared minus 8t. So because this can cancel out, so it's just a constant. So those 2 things have 0 expectations. And actually, we could have done, so what I do? I wrote a formula of total probability comparing my function at time 0 and at time t. But I can do the same at time s and time t. And then I will compare not 0 to wt, but I'll compare ws to wt. So we can do the same comparing ws and wt. So you write basically function f of z in omega s is equal to expectation for over O gamma from s to t, f of z in omega t. Well, omega s, omega t, so it's at domains we have at time s, at time t, omega minus gamma 0s. So if we do the same, you just get the same thing, but for increments of our function. Expectation of wt minus ws, the increment, or 0 is the expectation of wt minus ws squared minus 8t minus s. So basically the conclusion. So gamma is described, well, this gamma prime described by linear revolution with almost surely continuous wt. So that is from a priori estimates. From a priori estimate we will get that it's almost surely Gilder curve. So it's then almost surely linear revolution with continuous wt. So wt then, wt is an almost surely continuous process such that wt is a martingale. And wt squared minus 8t also are martingales, such that those 2 are martingales. which implies, so this is Paul-Levy theorem. So we used in the beginning Hans-Levy theorem, Kurn-Friedrichs-Levy, and this is Paul-Levy theorem, which implies that Wt is square root of 8 times Brownian motion. So we are done model with a priori estimates. And I can basically say that it's very error prone. So if you got the wrong boundary data or screwed up the calculation, then what in the end you get, in the end you would get some identities which don't make sense, which don't have solutions. So if I screw the calculation up and get here expectation Wt minus 1 equal to 0, that obviously there will be no such process. Or if, for example, if your process is not conformally invariant and you got some martingale from it you will see that it's not conformally invariant, you get certain bad things. So if it's conformally invariant, then what it means that you get some boundary value problem, you get big formula for it, but then everything nicely convolves. When you power series expand, the terms will be very nice. So the only bad thing can happen is that, for example, I do this 3 terms expansion and bumps one of them coefficient is 0, I don't get enough information. So that theoretically can happen. If, for example, here I plug in k equal 1, then I get no information in this place. So you need to have some generic observable and some generic points plugged in. So that's, but usually again it will happen, if it will happen that one of them is 0, then probably you can tweak it a little bit, then it is non-zero. So this is ideologically the main part, and once again comparing it to, so there is this Schramm, what Greg Lower calls Schramm meta principle, that if you have a curve which is conformally invariant, has Markov property, it has to be SLE. Unfortunately, we don't know how to use this meta principle in proofs, because to use it we need to prove that the curve is conformally invariant. And usually this is done via observables. And there is a stronger version of Schramm meta principle that if curve has one observable which is conformally invariant and Markov, then you can deduce that the curve is SLE and you can get kappa by doing a calculation. So it's even better. And of course you can imagine here that if I tweak a little bit instead of arcsine have something else, then I might just get different kappa. But there will be this rigidity that now, because I want to discuss them at least for one model. And also after that we will discuss a little bit of an SLE connection, because it's clear that there is this rigidity that if we get a martingale, well, it's kind of all fragile. If I destroy it a little bit, I get a contradiction. So it means that there are very few functions which can arise in that way, like this arcsine function. So indeed there are very few. One can easily classify them for SLE. You can start the other way around. You can ask what sort of function here, if it's a known function phi, can be a martingale for SLE 8. And when you solve, you'll get that actually essentially there are only 2 independent functions which are. One is arcsine, one is another one, and so it's only their combinations. So you can do it also the other way around. Yeah, by the way, this power series expansion is essentially, it's very much related to Ito calculus. You see that here in one form I got Wt squared and T, and they are from different terms in Ito calculus. One is from dt and one is from dB squared. So this is Ito calculus. So you can look at Ito calculus like we have the usual Newton calculus and Leibniz calculus. So you can either write derivatives and formulas, so you can do infinitesimal things and write plus something epsilon squared. So Ito calculus is very nicely thought of in terms of infinitesimal. And you have 2 infinitesimal entities, dt and dB. And there is a property dB squared is equal to dt. So that's maybe the best way to see it. And here essentially what we are doing, we are playing this infinitesimal calculus. And why it's infinitesimal? Because I say that dt, so t is small, but point c and point z are very far away. It's the same as saying that c and z are distance 1, but t is very small. And then I do this power series expansion, and Loeffler evolution somehow is built in, and well, you see I got a squared very much like it did. Okay, so next lecture is on Friday, And then probably then there are 2 lectures, 2 Fridays missing because of Easter. So let's maybe have one Monday before, just in case we'll have to miss some lecture later. And then we'll have a fairly long Easter break. Okay, thank you.